7 visitors are approaching Earth. A headline that sounds impossible, but it's real. By late 2025, 7 sizable comets will converge on the inner solar system in just 6 months, an occurrence so rare that leading surveys like Pan-STARRS and ATLAS have never logged anything close. Nestled among them is 3I/Atlas, only the third interstellar comet ever detected, its exotic chemistry and vast green coma making it the ultimate cosmic wildcard. The odds of this happening by chance? Less than 0.5% per decade. Is it just astronomical coincidence, or are we seeing something that breaks the rules of our sky? The answers, and the risks, start here. Every night, a silent network of digital eyes sweeps the sky. These are the world's automated comet hunters, Pan-STARRS, ATLAS, and their kin. Perched atop remote mountains in Hawaii, Chile, and South Africa, these telescopes scan nearly the entire sky, night after night, capturing faint glimmers that would escape the sharpest human observer. Their cameras are sensitive enough to spot objects as dim as magnitude 21, far fainter than Pluto ever appears from Earth. Each image is a mosaic of millions of stars and galaxies, but the real prize is movement, a single pixel drifting from frame to frame, betraying the presence of a new comet. The process is relentless. Pan-STARRS and ATLAS operate on a cadence that covers most of the sky every 2 to 3 nights. Their software compares each new image against a digital memory of the cosmos, flagging anything that has shifted. Once a candidate appears, a chain reaction begins. Automatic alerts, rapid follow-up by telescopes worldwide, and a race to confirm the discovery before it fades into the background noise. This digital vigilance has changed the game. 20 years ago, discovering a comet meant months of patient skywatching and a bit of luck. Now, the number of finds has doubled almost every year. Faint, distant visitors that once slipped by unnoticed are now catalogued, tracked, and analyzed in real time. The Minor Planet Center logs each detection, building up a census of icy wanderers that grows by the hundreds. But for all this power, even the best surveys rarely catch more than a couple of bright comets in a single season. The clustering of 7 significant comets in late 2025 pushes the limits of what these systems were designed to handle. Engineers and operators, usually content to let the algorithms run, are now glued to their monitors, watching as the data pipeline lights up with more comet alerts than anyone thought possible. For the first time, the machines are struggling to keep up with the sky. Before we dive deeper into this celestial traffic jam, it pays to have a quick cheat sheet. Comet science comes with its own set of terms, but most are easier than they sound. Perihelion is simply a comet's closest approach to the Sun, the point where sunlight does its work, turning a frozen nucleus into a showpiece of gas and dust. The word pops up in every comet forecast for a reason. It's when the action happens. Distances in the solar system get big fast, so astronomers use the astronomical unit, or AU, as shorthand. 1 AU is the distance from Earth to the Sun, about 93 million miles, or 150 million kilometers. If a comet's perihelion is 0.25 AU, that means it's a quarter of the way from the Sun to Earth. For skywatchers, the closer the comet, the better the odds for a bright display. Speaking of brightness, the magnitude scale is the astronomer's go-to. Here's the trick. Lower numbers mean brighter objects. A magnitude of 6 is the faintest most people can see without optical aid under dark skies. A magnitude of 3 or 2? That's bright enough to catch the attention of anyone stepping outside at dawn or dusk. Some comets, with a little luck, can even outshine the brightest stars. Then there's the matter of tails. Every comet grows at least 1 as it nears the Sun, sometimes 2. The dust tail is broad and pale, made of tiny grains pushed away by sunlight. The ion tail is straight and blue, built from charged gas swept directly by the solar wind. Think of it as a windsock for space weather. Occasionally, a solar storm will snap this tail clean off, only for it to regrow in a matter of hours. These tail disconnection events are rare, but with so many comets crowding the inner solar system, 2025 could deliver more than one live on camera. Keep these basics in mind. They'll help decode every headline, every sky chart, and every surprise the 7 visitors have in store. Statisticians working with comet survey data sometimes joke that the universe is stingy with surprises. In a typical 6-month stretch, the odds say we should expect 2, maybe 3 comets bright enough for backyard telescopes. The rest are faint, distant, and destined for the Minor Planet Center's archives. But late 2025 throws those expectations out the window. 7 significant comets, each with perihelion packed into a single half-year, have set off alarm bells in every Monte Carlo simulation run by comet population modelers. The numbers are stark. Over the last decade, digital surveys have pushed the detection rate of faint comets to new heights. Yet, even with the best technology, simulations show that a cluster of 7 in one season is a statistical outlier. When researchers feed real survey sensitivity and comet population estimates into their models, the median expectation is just 2 or 3 per half-year window. The chance of 7? Less than 0.5%. Some runs spit out odds closer to 1 in 1,000 years for a grouping of this brightness. The rarity isn't just a product of better cameras or more vigilant software. Bright comets are governed by the physics of their orbits and the randomness of when they get nudged sunward. Survey efficiency can find more faint wanderers, but it doesn't conjure up a septet of major visitors. The 2025 lineup stands apart from anything logged in the digital era, and even the old photographic records struggle to find a rival. For data scientists, this is the kind of anomaly that demands a second look. Are we seeing the aftershock of a distant collision? A fluke of Oort cloud dynamics? Or just a cosmic coincidence so rare it almost feels scripted? Whatever the cause, the numbers are clear. 2025's comet traffic jam is as close to winning the celestial lottery as modern astronomy has ever come. Some comets slip through the solar system almost unnoticed, their faint glow lost against the background of stars. Among the 7 visitors of 2025, 2 fall into this quiet category: C/2022 Pan-STARRS and 240P/NEAT. Pan-STARRS reaches perihelion on July 31st, looping in at approximately 3.82 astronomical units from the Sun, well beyond Mars, closer to Jupiter's orbit. At that distance, sunlight barely stirs the icy surface. The result is a modest coma, visible only through telescopes with sensitive detectors. Most backyard observers won't catch more than a dim smudge, even on the clearest nights. 240P/NEAT, another returning traveler, makes its pass on December 19th at 2.12 astronomical units. That's still twice as far from the Sun as Earth sits, and it shows in the brightness. This comet has made the journey before, each time offering a low-key encore for those willing to chase it down in the winter sky. For both objects, the main audience is a dedicated group of amateur astronomers, logging observations, stacking images, and comparing notes online. Their patience fills in the faint end of the comet census, ensuring that even the quietest visitors are counted. While these 2 comets won't steal the spotlight, they remind us of the full spectrum in the 2025 lineup, from telescopic whispers to headline grabbers. Their presence sets the stage for the brighter, more dramatic arrivals still to come. For anyone who's ever stepped outside and wished for a comet bright enough to rival the stars, late 2025 offers more than just a faint hope. 3 of the 7 visitors, Swan, Atlas K1, and Lemon, are shaping up to be true crowd pleasers, each bringing its own promise of spectacle. Swan, officially known as C/2025 R2, swings in for its closest approach to Earth on October 21st, passing just a quarter of an astronomical unit away. That's about 37 million kilometers, close enough for the solar wind to whip up a dramatic tail and bright enough that even casual skywatchers might catch it at dawn with the naked eye. Outgassing models predict Swan could reach magnitude 2 or 3, a brightness that turns comet watching into a neighborhood event. Just weeks later, Atlas K1 barrels in, reaching perihelion on October 8th, well inside Mercury's orbit. The intense sunlight at 0.33 astronomical units is expected to kick its activity into overdrive, unleashing powerful jets of gas and dust. Astronomers are watching for a sprawling tail and the kind of unpredictable outbursts that make for headline photos. Then comes Lemon, C/2025 A6, making its closest pass on November 8th at just over half an astronomical unit from the Sun. Forecasts suggest it could brighten to magnitude 4, possibly even 3.5, making it visible at dusk in the northern hemisphere and a prime candidate for backyard binoculars. Each of these comets carries a different energy. Swan's close approach, Atlas K1's inner orbit fireworks, and Lemon's classic evening display all offer a shot at something rare. A comet so bright you don't need a telescope to join the show. Not every comet in the 2025 lineup is best observed from Earth. Some, like 414p/stereo, are practically invisible to backyard telescopes, but they are front and center for a fleet of spacecraft stationed around the Sun. On September 27th, 414p swings just over half an astronomical unit from the Sun, closer than Venus, but its orbit keeps it tucked in the Sun's glare from our vantage point. This is where missions like SOHO and Stereo take over. Their cameras, designed to monitor solar storms, catch comets as bright streaks in the solar corona, revealing details about activity that ground-based observers miss entirely. Mission teams at NASA and ESA are already juggling schedules, weighing which comets get precious instrument time. The October sky will be crowded, not just with comets, but with scientific priorities. Swan and Atlas K1 promise dramatic tail displays, while 3I/Atlas, the interstellar newcomer, demands close scrutiny during its brief passage. Each spacecraft has a limited field of view and can only point at one target at a time. That means tough choices. Focus on the rare interstellar chemistry of 3I/Atlas, or chase the evolving tails of Swan and Atlas K1 as they respond to solar storms. Heliospheric images and coronagraphs will track tail disconnection events in real time, capturing the moment when a solar eruption severs a comet's ion tail. These observations aren't just for show, they reveal how the Sun's magnetic field sculpts comet tails and, by extension, the invisible space weather that fills our solar system. In 2025, spacecraft and ground-based telescopes form a coordinated network, each covering angles the other can't reach, ensuring that no visitor slips by unstudied. 7 comet arrivals, all squeezed into a single calendar stretch. From late July through December, the inner solar system becomes a cosmic thoroughfare. The first visitor, Pan-STARRS, makes its distant pass in July, barely stirring the detectors. Then the pace quickens. By September, Swan is closing in, followed closely by 414p/stereo, which slips past the Sun while spacecraft scramble for vantage points. October turns crowded. Atlas K1 dives toward the Sun, outgassing furiously inside Mercury's orbit. Just days later, 3I/Atlas, the interstellar outlier, threads its hyperbolic path past Mars, its coma swelling to hundreds of thousands of kilometers across. Lemon follows in November, drifting into dusk skies with the promise of naked eye brightness. Finally, in December, 240p/NEAT rounds out the sequence, a quiet encore for those still watching. Stacked on a timeline, these arrivals look less like a random scatter and more like a cosmic cue. Each comet's perihelion falls within weeks of the next, leaving little downtime for astronomers or skywatchers. The compressed schedule means overlapping observation campaigns, crowded data pipelines, and a steady stream of fresh images. For the first time, the challenge isn't finding a comet, it's keeping track of which one you're seeing. This 6-month squeeze turns the sky into a living laboratory, where the mechanics of coma, tail, and solar wind play out in real time, sometimes with multiple comets in the same frame. The stage is set for a season of tail physics and solar drama, unlike anything in recent memory. Every comet in the 2025 lineup brings a signature feature to the night sky, but nothing stands out more than the twin tails that trail behind. The difference comes down to what's being pushed and what's doing the pushing. The dust tail is broad and curved, made of microscopic grains swept away from the comet's surface by the force of sunlight itself. These tiny particles scatter sunlight in all directions, giving the dust tail a pale, sometimes golden glow that can stretch for millions of kilometers. It fans out gently behind the comet, following the curve of its orbit like a luminous wake. The ion tail, on the other hand, is a straight, narrow blade of electric blue. This tail forms when ultraviolet light from the Sun strips electrons from gas molecules in the coma, turning them into ions. The solar wind, a stream of charged particles racing outward from the sun, grabs these ions and hurls them directly away, no matter which way the comet is moving. The result is a tail that always points straight from the comet to the sun's opposite side, often with a sharper edge and a more vivid color than the dust tail. For sky watchers, the visual cues are clear. Dust tails are wide, soft, and often yellowish or white. Ion tails are thin, straight, and blue. Each tail tells a different story about the forces at play, and both are vulnerable to the sun's moods. When a solar storm sweeps through, the ion tail can be sliced off in a heartbeat, an event that reveals just how dynamic and unpredictable these cosmic visitors can be. Solar storms don't just light up the auroras, they can turn a comet's graceful tail into a battleground. When a powerful coronal mass ejection, or CME, sweeps through the inner solar system, it drags the sun's magnetic field along for the ride. If a comet happens to be in the crosshairs, the results can be spectacular. The ion tail, that straight blue blade pointing away from the sun, can be severed in a matter of minutes. This isn't a gradual fading or a slow unraveling. One moment, the tail stretches for millions of kilometers. The next, it's been sliced clean off, left drifting in space while the comet forges a fresh one. The most famous example came in April 2007, when NASA's stereo spacecraft caught Comet Encke mid-disaster. A CME slammed into Encke's ion tail, snapping it away in real time. The footage became a case study replayed in heliophysics seminars and comet watcher forums alike. Scientists call these events magnetic reconnection, a sudden reconfiguration of the magnetic field lines that drags the tail's ions out of alignment. For a few hours, the comet is left exposed, its tailless state a visual signpost of the sun's invisible power. With 7 comets crowding the ecliptic in late 2025, the odds of catching another live tail snap are better than ever. Heliophysicists and amateur astronomers alike are on alert, watching for the telltale signs: a sudden kink, a break, or a ghostly wisp left behind. Each event offers a front-row seat to the sun's reach, a reminder that space weather isn't just theory, it's written across the sky in real time. Comet tails don't just make for pretty pictures, they double as instant space weather reports. The reason? Geometry. In late 2025, most of the 7 comets are threading paths close to the solar system's ecliptic plane, the same flat sheet where Earth and the other planets orbit. This shared highway means that when the sun launches a coronal mass ejection, or CME, the odds of a comet being in the crosshairs go way up. It's a matter of simple alignment. With so many comets clustered near the ecliptic, each one spends more time in the firing line of solar storms. Forecast models run by heliophysicists show the numbers clearly. In a typical year, a bright comet might have a 10 to 20% chance of a visible tail disconnection during perihelion. With 7 comets stacked along similar orbital lanes, those odds multiply. Statistically, the 2025 season could deliver several tail snap events, potentially even 2 or more in the same week. For observers, this means more than just a crowded sky. Every CME that sweeps through the inner solar system is a roll of the dice. If the timing lines up, the sun's magnetic field will slice through a comet's ion tail, producing a sudden break, a visual cue that space weather has struck. With so many comets in prime geometry, the coming months promise a rare chance to watch the sun's invisible hand at work, written in blue streaks across the dawn and dusk. The numbers coming in from the world's largest telescopes are staggering. Astronomers using the Hubble Space Telescope and the James Webb Space Telescope have measured the coma of 3R/Atlas, its glowing envelope of gas and dust, at nearly 700,000 kilometers across. That's not a typo. This single comet's coma is nearly half the diameter of the Sun and more than 50 times wider than Jupiter. Images show a diffuse, greenish sphere that dwarfs the rocky nucleus at its heart, a tiny fragment lost in a cloud that could swallow planets whole. But size is only part of the story. What truly sets 3I/Atlas apart is its activity. As sunlight strikes the surface, jets of gas and dust erupt from the nucleus with astonishing force. Measurements from JWST and ground-based observatories put the dust ejection rates at 6 kilograms per second for fine grains, about the weight of a bowling ball every second, and up to 60 kilograms per second for larger chunks. These jets carve out fans and streamers in the coma, sometimes shifting from hour to hour as new vents open and close with the rotation of the nucleus. The result is a living, breathing structure, constantly reshaped by sunlight and space weather. Imaging teams from Gemini South and Palomar Observatory have spent countless nights tracking these changes, stacking exposures to tease out subtle details in the jets. Their work reveals a comet that is anything but static. The jets flicker and pulse, sometimes tracing arcs hundreds of thousands of kilometers long. Each outburst adds fresh material to the coma, feeding the tails that stretch far behind. Even at a distance of more than 1 astronomical unit from the Sun, 3I/Atlas is putting on a show that rivals the most active comets ever observed. The scale of this physical presence is hard to grasp. For astronomers, it's a rare chance to study the mechanics of cometary activity in real time, using some of the most advanced instruments ever built. Every new image, every measured jet, adds another piece to the puzzle, laying the groundwork for the next big question. What exactly is this visitor made of? What happens when a comet from another star system reveals a chemistry no one expected? Spectroscopists working around the clock with JWST and SPHERX have found that 3I/Atlas is a rule breaker. Unlike most comets, where water vapor dominates the show, this visitor's coma is flooded with carbon dioxide. The numbers are hard to ignore. For every molecule of water, there are 8 of CO2, an 8-to-1 ratio that sets a new record for any comet measured so far. The usual script for a bright comet says water ice should take center stage, vaporizing as sunlight hits and forming the classic glowing tail. But in 3I/ATLAS, water is almost an afterthought. Instead, CO2 jets erupt from the surface, painting the coma green and fueling a debate among planetary scientists. Was this comet formed in a frigid zone beyond the reach of its home star, where carbon dioxide could freeze out in bulk? Or is there a thick, insulating crust hiding pockets of water ice, waiting for the right moment to burst free? The answer is still up for grabs, with teams poring over every spectrum to tease out the truth. This chemistry isn't just an academic curiosity. If 3I/ATLAS is shedding CO2-rich dust, the particles it leaves behind could be unlike anything Earth has ever seen. And there's a twist coming. N-body simulations show that after perihelion, the dust trail from this interstellar traveler may cross Earth's orbit in mid-2026. Meteor scientists are already mapping the possible intersection, drafting plans for radar and airborne campaigns to catch even a single grain of true interstellar dust as it burns up in our atmosphere. If successful, these efforts could deliver the first direct sample of material forged around another star, a chance to analyze isotopes and molecules untouched by our own solar system's history. For now, every new observation of 3I/Atlas is a ticket to the frontier of planetary science, where the stakes are nothing less than rewriting what we know about the chemistry of worlds beyond the Sun. Rumors spread faster than comets. In the weeks leading up to the 2025 Comet Parade, social media timelines fill with warnings, dramatic claims, and a steady stream of doomsday predictions. But here's what the data actually say. Every comet in the 2025 lineup follows a well-mapped path, calculated and recalculated by professional astronomers using the world's biggest telescopes and the Minor Planet Center's global database. None comes close to intersecting Earth's orbit, let alone posing a risk of collision. The closest approach, by Comet Swan, puts it about 37 million kilometers away, more than 90 times the distance to the Moon. The rest pass even farther out, their trajectories bending gently around the Sun, guided by gravity and nothing more. Expert panels from NASA, the European Space Agency, and independent research groups have reviewed the orbits, checked for any possible perturbations, and published their findings in open-access journals. The verdict is unanimous. There is no physical mechanism by which this comet cluster could trigger earthquakes, storms, or any of the disasters trending online. Gravity works the same as it always has. Comets are icy leftovers, not cosmic wrecking balls. The only thing they're likely to influence is the number of people looking up at dawn and dusk. The message is clear. This is a rare sky show, not a threat. The best way to experience it is with a sense of wonder, not worry. For those eager to see a comet for themselves, the next step is knowing where and when to look. Step outside on October 21st, just before sunrise, and you might catch the sky's main event. That morning, Comet Swan makes its closest approach to Earth, about 37 million kilometers away. No telescope required if you have dark skies and a clear eastern horizon. Look low in the east, a little before dawn. If predictions hold, Swan could shine as bright as magnitude 2 or 3, rivaling the brightest stars. Its tail, shaped by the solar wind, may stretch across a good portion of the sky. A rare treat for anyone up early enough to see it. A few weeks later, dusk takes the spotlight. From November 6 through 12, Comet Lemon slides into view in the western sky after sunset. This is the classic evening comet. No need to wake up early, just find a spot with a wide, unobstructed view to the west. Lemon could reach magnitude 4, possibly even brighter if activity surges. Under rural skies, that's enough for the unaided eye. In town, binoculars will help pick out the fuzzy glow above the horizon. The best time is about 30 to 60 minutes after sunset, before the comet dips too low. For both events, a pair of binoculars unlocks more detail, showing the coma's soft glow and the first hints of a tail. A small telescope takes things further, revealing structure in the tail and subtle color changes. But you don't need fancy equipment. A printed star map, a phone app, or even a compass can help you find the right direction. Dress for the weather, bring a friend, and give your eyes time to adjust. Patience pays off. Comets can brighten or fade unpredictably, and the view changes from night to night. In a year when the sky is delivering more than its share of surprises, these windows are your invitation to join in, no experience required. The only real requirement is the willingness to look up. The clustered arrivals have no known precedent in over a century of recorded comet data. Scientists note that while the dust trail of 3I/A TLAS may intersect Earth's orbit in 2026, no impact hazard exists according to published orbital models. However, why so many comets appear in one season remains unsolved, with current population models unable to fully account for this spike. The evidence points to a rare convergence shaped by both random chance and improved detection methods. As 2025 and 2026 unfolds, the record will show not just a statistical anomaly, but a unique opportunity for observation and scientific discovery, documented in real time for future analysis.